Hello, waves 3, standing waves. What do we mean by standing waves? Well, they're also sometimes called stationary waves because they appear not to move. Now that might be a bit abstract for you, but when we start looking at them you'll get what we mean by that. In fact, they are two waves moving in opposite directions, so one moving one way, one moving the other way. They need to be symmetrical, periodic waves. That means they have to be pretty much identical with equal amplitude and frequency, therefore have the same wavelength but travelling in opposite directions. Okay? And what we get is constructive and destructive interference occurs, and it occurs in a regular pattern, and that's why we get a thing called a standing wave. Now the destructive interference occurs at evenly spaced points along the medium and occurs all the time. These points are referred to as nodes. So that's where you get destructive interference. Between the nodes are points where the waves are constantly reinforcing each other and producing a maximum amplitude, and that's where you get constructive interference, and that's where we call antinodes, and that's where you get your supercrests and your supertroughs occurring. So let's just walk our way through one, and then I'll do a couple of animations to highlight, give you some motion. So what we're trying to show here in a very small diagram is two waves. One's moving to the left and one's moving to the right. One's dashed and one's a solid line. And the blue line is the resultant. And N stand for nodes and A stand for antinodes. So here we have a crest and a crest interfering with each other, and the resultant is a supercrest. Trough and a trough, supertrough. Nothing and nothing, so you get a node. Alright, now the pulses have now moved a quarter of a period. So that means that which one's moving which? The dashed one's moving to the left, so instead of having a crest here, we've now got a midpoint. Okay, and they've moved on. Now, what's the resultant in this case? Well, the resultant is the nodes are still nodes, but the antinodes are now swinging, and so they are now on the midpoints. And we'll see in the next slide, the antinodes have swung. When I say they're swinging, it means that they're going here. We're going from a super trough to nothing to a super crest, and this is half a period. Okay, and so the nodes are still nodes. Again, the blue line is the resultant, but the antinodes are swinging between supercrests and supertroughs, and if we go on one more, we're back into the transition phase. Okay, and there's a couple of things I'll show you now. Let's see if I can bring them up. I'll bring up the picture. Okay, now we've got two pulses, a blue one and a green one, and the yellow pulse is the resultant. Now notice that they're identical, the blue and the green, they're just moving in opposite directions. So hopefully this works. Let's make it a little bit bigger, that will probably stuff it up. Here we go. It works. And so this is our standing wave. So here we have a node, there's another node here and another node here, and we're swinging between supercrests and supertroughs. Now I can't speed that up, but you get the idea. So that wave, this waveform, doesn't appear to be moving left or right. It's pretty stationary, isn't it? But it is still a wave. And it's the culmination of two waves interfering with each other. Pretty cool, hey? Alright, so I'll pause that, get that down there, and there's another animation, which is of course the one we were using before, this guy. And what we're doing here, let's make it a fixed end. If we oscillate this, okay, so we start it, we're sending down pulses, and the pulses are being reflected back, and they're interfering with each other. Now you can see there's a sort of standing wave here. Now strictly speaking, it's pretty close, because you can see this point here is a node. This one, there's a node there, there's a node there, and then we have the antinodes, and the antinodes, and the antinodes. Now we'll learn later on, when we start using some equations, that if we vary the frequency, we'll lose the nice regular pattern. Okay, and we just get a sort of random, oh that's not, well yeah, it's, you can see that the nodes and antinodes aren't stable, and so we're getting a sort of random interference. And if we increase it up, and there's only certain frequencies for every situation, there's only certain frequencies of the interfering waves that will give you a standing wave. So here we can see it sort of looks like a standing wave, and then it collapses into a chaotic pattern. So it's not a stable structure, and so this isn't called a standing wave. It has to be a very stable structure. Now I can change it to a loose end, and we can get the same thing happening. I can increase the amplitude, I can vary the frequency. So this again will be on the one note hopefully, and you'll be able to have a go at it. Right, now how do I minimize this all down? Let's see, let's go up here. Right, next. So this is another diagram. This is demonstrating the fixed end. So we can have two waves from two different sources, or one wave could be a reflected wave, and we would get the standing wave, and this is our mean position, and there's our antinodes and our nodes. So now you can do all these questions. Joy. And in the next video we'll look at Huygens principle. See ya.